Greetings, my dear students. My name is Mr. Mahdi Shur, and today I'm going to explain to you a lesson in physics which is pretty interesting, and it is called harmonic motion. The objectives of today's lesson are very simple. I don't want you to lose yourself in what is written on the PDF file. Right now, I'm going to explain to you what we are going to do. We are going to explain the physics of oscillation, what is oscillation, and then I'm going to tell you its characteristics to describe it for you. Then I am going to use intuitive mathematical reasoning in order for you to understand the equations that govern a certain type of harmonic motion, a certain type of oscillatory motion. We are going to understand the graphs, and then of course we are going to understand why what we are studying is very important. We are going to bridge between harmonic motion and what exists in nature. First of all, of course, we have to understand what is oscillatory motion. Now, an oscillatory motion is a to and fro motion between two extreme positions during a constant interval of time. I know this might sound overwhelming, but listen to me. Is the girl in this picture oscillating? Is she going in a to and fro motion between two extreme positions, the highest position from the back and the highest position from the end? Yes, she is. Then the girl is oscillating. So the girl in this picture is oscillating because she's going in a to and fro motion between two extreme positions. Now let me go to something more physicsy. This mass is oscillating between those extreme positions. It is also going in a to and fro motion between two extreme positions. Okay, what about this spring in here? I push it and I leave it, and it is also going in a to and fro motion between two extreme positions. And so it is said that this block is oscillating. Now there are a lot of types of oscillation in nature. What we are interested in today is called the free undamped mechanical oscillation. Now, the title might seem a bit long, but let me break it down to you. Free meaning that we only induce a certain push to it, and then we leave it, and it's free. It does the oscillation alone, as we did in this pendulum over here. I pushed it up, I moved it up, and then I left it. And it's oscillating alone, and this is why it is called the free. Now, undamped meaning that it will oscillate forever without any effect of friction. It will keep on moving forever, and this is why this is called free undamped mechanical oscillation. Now we are going to discuss the characteristics of the free undamped mechanical oscillation, and those are, as you are familiar with those terms from previous years, the period measured in seconds, the frequency measured in hertz, and the amplitude, which is measured usually in meters. And so what is the period, the frequency, and the amplitude? The period is the time constant, is the constant time taken by the oscillatory motion to repeat itself. A frequency is the number of oscillations performed per unit time, and the amplitude is the maximum displacement of the oscillating object from its equilibrium position. Now, of course, those are just words. Words are not understandable. Images are understandable. Imagination is understandable. And this is why I'm going to show it. This is why I'm going to use this as an example. I will raise this to a certain amplitude, and I'm going to leave it. And now you are going to see a blue line that is called the period trace. Goes and returns. This is one period. Goes and returns, and this is called one period. And you see the time taken to perform this period is called to perform this oscillation is called the period. In question 1, in your own words, define period and frequency. Those you do them from your own understanding after you've studied. And what is the SI unit of each? Those are clear. Part 2, write the mathematical relationship between period and frequency. We can state that since t, the period, is the time taken by one oscillation, so it is the total time divided by the number of oscillations, where the frequency is equal to number of oscillations per unit time, and it is clear from both of the relationships that t is equal to 1 over f. Part 3 states that if the frequency of a wave doubles, what happens to the period? And so he's telling us that f prime is equal to 2 of the initial frequency f, And we want to find the relationship with period. And we know that t is equal to 1 over f, or f is equal to 1 over t. We can substitute 1 over t prime is equal to 2 1 over t. And with some very simple mathematics, we can reach the conclusion that t prime is equal to half the initial period. And so when the frequency doubles, the period is halved. Going to question number 2. Two different pendulums, A and B, are oscillating. Pendulum A completes 20 full cycles in 10 seconds. And pendulum B takes 0.4 seconds to complete a full cycle. Without any precise calculations, which pendulum has a higher frequency? Since he asked without any precise calculation, we're going to have to be a bit creative here. So we can't basically calculate the frequencies and compare them. Let's go back to the fundamental definition of the frequency. We know that the frequency is equal to the number of oscillations in a certain amount of time. So for pendulum A, there is 20 full cycles in 10 seconds. However, for pendulum B, there is 1 cycle in 0.4 seconds. And so for 10 cycles, it is going to take how much? X is equal to 0.4 multiplied by 10 divided by 1, and X is equal to 4 seconds. And so now we know that that B will do in a matter of 10 seconds. It's going to do in a matter of 4 seconds. It is going to do 10 cycles, while A is going to do 20 cycles in those same 10 seconds. And so A is doing more cycles, which means that the n of A is larger than the n of B in the same amount of time. Now we know that the number of cycles done by A is larger than the number of cycles done by B. The number of cycles done by A is larger than those done by B at the same time. So the time is equal, TA is equal to TB. Thus, we can conclude that the frequency of A is bigger than that of B. Which one has a longer period? We know that the frequency and the period are inversely proportional. So if FA is bigger than F of B, this means that 1 over TA is bigger than 1 over TB, and thus T of A is smaller than the T of B. Question number 3. A surfer notes that the time interval between the crest of one wave and the crest of the next wave is 8 seconds. While he gets 2 meters above the water level. State the physical meaning of the numbers collected by the surfer. And so we have certain waves, and the time it takes for the crest of the wave to pass the same point twice is 8 seconds. And so from here to here, the time is 8 seconds, which marks a full oscillation from crest to crest. And the maximum distance above the water is 2 meters. So what is the physical meaning of each one of those? Since the time is the time between a crest and a crest, it is obviously the time for a full cycle, and so it is a period, and so we know that the period is equal to 8 seconds, while the amplitude above the water level is 2 meters, and thus 2 meters is an amplitude. Draw a graph xt representing those data. And it is clear that this is our lovely graph. Or if we could draw a new one, it's going to be like this. One, two, minus one, minus two. It's going to raise to one, to two, go back to minus two, and then go back to one, while those zero, two, 4, 6, 8, 10. And now we are going to find the frequency of motion in the last part. It is very easy since we have already found the period. We can state that the frequency is equal to 1 over period, 1 over 8 hertz. And now we are going to discuss the elastic pendulum and precisely the horizontal elastic pendulum. I have a little thing, a motivational sentence that I've written to you here, and it states as follows. Simplicity can be unjustly judged as shallow, but in it might exist universal truth. And the meaning of this sentence, hopefully, I'm going to explain to you by the end of this session, because I want you to look at those problems beyond them being just a spring and mass oscillating around a point. I want you to be able to connect the mathematics and the understanding and the ideas of those problems to much larger ideas that exist in the universe. Not saying that those might not be interesting, of course they are interesting, but I want to give you the key to understand something that truly exists in the world and how to use those simple principles in order to understand much deeper ideas that exist in the universe. Let's go to a simulation, and I simply want to show you what is a horizontal elastic pendulum. I push it to a certain amplitude and I leave it, and it will go forever in and out to that certain amplitude that it was initially put at. 1 meter minus 1 meter, 1 meter minus 1 meter. Now, of course, this is easily seen as an oscillation. It is a to and fro motion between two extremities. So it is an oscillation, and it is an undamped free oscillation because we've only put it at a certain point and left it. It's free, it's moving alone, and it doesn't have any frictional forces that are decreasing its amplitude. But Mr. Mahdi, how are we supposed to understand the mathematics, or how to describe this that you're telling me about? What do you mean to and fro motion? How can I get information from this? And today I'm going to explain to you in a way that is very intuitive to you to understand how we are going to set the solution of this mechanical system that we have. To and fro motion is, we are going to relate the to and fro motion to cosine and sine. First of all, we have to identify what is the shape of motion. It's very clear that to and fro motion is a repetitive motion. It goes from amplitude to minus amplitude, amplitude to minus amplitude. And we think what kind of function resembles this motion, and it is clear that the cosine function does that. And the sine function does that too. For the sake of not mixing the ideas up, let's just take the cosine now. It goes from 1 to minus 1, 1 to minus 1, and forever repeats itself. And so now we can describe the movement of the position as a function of cosine that is moving with respect to time. But Mr. Mahdi, not all functions move to 1 and minus 1. What if the pendulum is moving between 4 meters and minus 4 meters, or 3 meters and minus 3 meters, or any number, whatever the amplitude? And for this, my dear children, we have a solution, a very beautiful solution. Let's take now the cosine function and choose the 2 cosine or 4 cosine. It's clear that when we multiply this function by a certain number, the amplitude changes, the extremity of this function changes, and so we can set now that x is called the amplitude multiplied by this cosine function of time. But again, Mr. Mahdi, not all functions move at the same speed. And for this, we introduce the following functions. As you can see, the green function, which is cosine x, is moving slower than cosine 2x. Meaning cosine 2x is changing faster. It is going in this zigzaggy pattern and more often than cosine x. Again, this is cosine 2x, changing zigzaggy a lot, and this is cosine x, changing zigzaggy less more often, and this is cosine 5x. It's doing a lot of zigzags motion, and so the change with time is affected by a certain number that is put inside the cosine, and this is that we are going to call cosine wt. We have formed the solution of the mechanical system. But again, there is a small question that I want to answer. What if the motion did not start at 0? What if it did not start at A? What if it did not start at, what if the motion did not start at A or minus A? Because this solution over here suggests that if the time is equal to 0, then most definitely x was equal to A. But what if at the time equal to 0, I pushed it to a certain, I pushed the block to a certain A, and I left it, but I started my calculations not on that A. I started the time not on that A, but on a different interval of on a different moment in time. And so this difference in measurement is represented by a value that we call phi, or the phase constant. And this is put besides the cosine as plus a certain number. Now, of course, you can see it in this graph. If I create a certain input, cosine x, let's put a new function, cosine x plus 3. You can most definitely see that the new function shifts into a new position. This was here, however, this is here. It shifts to the left or right. So where we start differs. And so this is only the job of phi. It tells us where did we start measuring the time. Now that we have understood the form of the solution of position, meaning that we know the position at every instant in time, we've understood the form of the solution, we have to become more precise. First of all, we have to understand what exactly is W. We've seen from the graphs that W affects the number of zigzags that occur in a certain amount of time, meaning if there are more zigzags, meaning there are more oscillations in a certain time, it means that it certainly is some type of frequency. But we are going to find now, to be more precise, and find the differential equation of the entire motion. And for this, I want you to be very focused with me. First of all, let us take a certain pendulum. shifted from its equilibrium position a distance a. We know that the mechanical energy of this pendulum is represented as the kinetic energy plus the elastic potential energy. We also know that this is undamped, and so the frequency is most definitely equal to 0. Thus, the mechanical energy is conserved. The mechanical energy is equal to a constant. We can now say that the mechanical energy is equal to half mv squared plus half kx squared. However, since the mechanical energy is a constant, we can safely say that the derivative of the mechanical energy with respect to time is equal to 0, since the derivative of a constant is equal to 0. And so we can derive the full formula and have it equal to 0. Now, a quick refresh on mathematics. You know that if we have u to the power of n and we want to find its derivative, the formula is n minus 1 multiplied by u. And so we can state here that half m is a constant, of course it remains on the outside. The derivative of the velocity square is v to the power of 1 multiplied by the derivative of velocity, plus half k is a constant. K is the spring constant, of course. And it is 2x prime with the same logic is equal to 0. Now 2. We can now say that v prime plus kx prime is equal to 0. You see now, since the equation, the differential equation must be in terms of x because the solution is for x, let's put v in terms of x. You know that x, the derivative of x is the velocity, and the derivative of velocity, which is double the derivative of position, is the acceleration. You're familiar with those formulas. And so we can replace x prime x double prime plus kx prime is equal to 0. We can take x prime as common. x double prime plus kx is equal to 0. Now the velocity obviously cannot be always equal to 0, and so, or else we don't have any motion, plus kx is equal to 0, and we finally reach the final form of the differential equation, dividing this by x double prime plus k over x is equal to 0, and we get this differential equation with this over here being, guess what, the w that we've been searching for squared. And so w squared is equal to k over m, or w is equal to radical k over m. We now take the final form of differential equation of simple harmonic motion, and it takes the form of x double prime plus w0 squared x is equal to 0, with w0 squared equals to k over m, and w0 equals radical k over m, and it is called the angular frequency, measured by radians per second. Now we are going to deduce from what we have calculated. We are going to deduce the physical quantities that matter to us during the measurement of any motion. So what are those physical quantities? If you drive in a car and you want to understand the the quantities that matter to the car, that would be where is the car, how fast is the car moving, and the acceleration of the car. If you're familiar with sports cars, they say it accelerates from 0 to 100 in 3.2 seconds or in 3.5 seconds. And so this is they are bragging about how fast can this car accelerate, and so acceleration is very important. How can we deduce those from the solution of the differential equation that we have found? We have found that the solution of x is simply equal to a cosine w0t plus phi. And we know that the velocity is simply the derivative of position. And so the velocity is equal to the derivative of all of this quantity. A quick math refresh is that cosine u, if you want to find its derivative, it is simply equal to minus u prime sine u. Minus u prime sine u. And so this is equal to minus a, derivative of this is w0, because the derivative of w0t plus phi is w0. This is a constant, and the derivative of time is simply 1. Sine w0t plus phi, and so v is equal to minus a w0 sine w0t plus phi. We also have that the acceleration is the derivative of the velocity or double the derivative of the position, and so a is equal to, also a quick math refresh, the derivative of sine u is u prime cosine u. So this is minus a w0, those are constants. Again, the derivative of w0t plus phi is w0, and so it is w0 cosine w0t plus phi. So the acceleration is equal to minus a w0 squared cosine w0t plus phi. The acceleration is minus a w0 squared cosine w0t plus phi. Now, from the three formulas that we have found, x is equal to xm or a cosine. Of course, don't forget that cosine can be sine. It's the same thing. It's just the phi differs, and where we started differs, but it would be the exact same operation of solving. w0t plus phi. V would be minus a w0 sine w0t plus phi, and the acceleration would be minus a w0 squared cosine w0t plus phi. Okay, now we have to understand the maximum values of velocity, acceleration, and position. This is clearly the maximum value of the position. It is the quantity that is previous to the cosine function, and so the quantity that is previous to the sine function is the maximum velocity, because if we take the maximum value of sine is 1, and so the maximum value of the sine function is equal to 1, and thus the maximum value of the velocity, of course absolute value, is equal to a w0. That the minus sign is does not really indicate anything about it's a scalar value of speed. It cannot be negative. And so this is the maximum value of the velocity. And the maximum value of the acceleration, A max, is also a w0 squared. However, this sign in here is pretty interesting. This sign appears no matter if we started with the cosine function at the beginning or the sine function in the beginning, which is not the same to say about this minus sign. This minus sign in here states that the acceleration is always opposite to displacement, or the acceleration being a restorative acceleration. Let's head to the laboratory and try to understand. If we push the block to a certain amplitude and we leave it, the restoring force of the spring is always opposite to the displacement, and here is the restorative force. As you can see, when the displacement is outward, the restorative force is inward. When the displacement is inward, the restorative force is outward. And so the green line and the red line are always, the green vector and the red vector are always opposite to each other. And the red vector represents the elastic force, but it can also represent the acceleration of the block, and thus the acceleration always has a negative sign because it is a restorative acceleration. Before beginning the problem that we want to solve, I have to explain a few things to you. And those are going back to the angular frequency W0, which we stated that it is equal to radical K over M. However, it is important to know that we also have a quantity called the proper period T0, which is equal to 2 pi over W0, and the quantity called the proper frequency, which is F0, of course, is 1 over T0, and so it is W0 over 2 pi. So now, let's put all of them together. Great. Let's go to the question now. We are now going to start with the first real problem of the day, and that is the application number 1. Consider the horizontal elastic pendulum in figure 8, which is the figure in the whiteboard, and the stiffness of the spring is K is equal to 10 newtons per meter. The mass of the block is 0.5 kilograms. And the block of center of mass G is displaced horizontally to the right by a distance of 10 centimeters and then released from rest. You see, now this is incredibly important. And why is that? It is because what he just stated are called the initial conditions, meaning where we started exactly. And if you remember, when I was talking about phi, I said that phi is the difference between where we started observing and measuring motion. And so those are most definitely related to phi, because it differs what were the initial conditions before we started measuring or observing. Those are that x was equal to 10 centimeters or 0.1 meters, and it was released from rest, meaning that the initial velocity, or x prime initial, was equal to 0 meters per second. He also stated that neglect all friction, and so the frictional forces are equal to 0. The mechanical energy of the system S. Okay, part 1. The mechanical energy of the system is equal to a constant, most definitely, since the friction is equal to 0, the mechanical energy is conserved. However, this tells us that we can calculate the mechanical energy at any point, and we would get its constant value. For this, I'm going to choose to calculate the mechanical energy at a point of which I know its kinetic energy or its speed, and its elastic potential energy or its elongation delta x. So the mechanical energy, that would be the initial timing, is equal to half mv0 squared, which is 0, plus half kx0 squared. And so the mechanical energy is equal to half multiplied by k, which is 10, multiplied by 0.1 squared, and we get the value of mechanical energy to be in joules, and that is 0.5. I'm sorry for this calculation mistake. This is 0.05 joules. For part 2, as at an instant t, the abscissa of x and the algebraic value of its velocity is v. Write the expression of the mechanical energy of the system in terms of x, v, m, and k. And so this is pretty easy to find. It is equal to Ek plus EPE. And so the mechanical energy of the system is equal to half mv squared plus half k x squared. Since he wanted it to be in terms of x, v, m, and k, here we have x, v, m, and k in the final answer. This is pretty simple. And so this is part A. Part B. Deduce the differential equation that governs the variation of x. I'm not going to do the differential equation again. It's the same that I've done before, using the fact that the mechanical energy is constant and that the derivative of the mechanical energy with respect to time is equal to 0. I'm going to do the exact same of what I've done previously in the session to reach the differential equation of x double prime plus k over m x is equal to 0. This is the differential equation of motion. Now we go to part C. Deduce the nature of motion. See, now it becomes interesting. We have stated that if the shape of the differential equation is similar to x double prime w0 squared x is equal to 0, then it is simple harmonic motion. And so this is the exact same shape, it being. And so w0 squared is equal to k over m. And then the motion, so those are the same. And so the motion is simple harmonic motion. Indicate the type of this oscillation. Since it is free and it is free from friction, we neglected the force of friction, then so the friction force is 0 and no intervention, then it is a free undamped oscillation. Part 4a. Verify that x is equal to this much is a solution of the differential equation. Since we have already found that the differential equation is as follows, we want to now prove that x is equal to xm cosine w0t plus phi is a solution, of course, given that W0 is equal to radical K over M. You see, now those questions can be tricky to understand, but they are very easy to execute. Let me explain to you the logic behind this. If you want to prove that a certain number is the solution of a certain equation, you simply plug it inside the equation and the equality should be correct, meaning as follows. Let me give you an equation that says x plus 1 is equal to 0. And I asked you, is x equal to 2 a solution? And so you take x equal to 2, you plug it in here, and so you get 2 plus 1 is equal to 0, and 3 is equal to 0. This does not satisfy the equality, and so no, it is not a solution. However, if I asked you, is x equal to minus 1 a solution? You plug it in, you get minus 1 plus 1 is equal to 0, and so 0 is equal to 0, the equality is correct, and then yes, this is a solution. The exact same logic follows here by us doing the following. We substitute the given equation inside the given solution inside the differential equation, and we should get 0 is equal to 0. And however, for this, since we already have that x is equal to xm cosine w0t plus phi, this is what we want to prove there is a solution. In the differential equation, we need to substitute x double prime. And so we have to find x double prime before substituting it in the equation. By x double prime is found by deriving x twice. And so we derive this being xm minus xm, the derivative of w0t plus phi is w0 sine w0t plus phi, and so x double prime is equal to minus xm, as we've done it in the acceleration, velocity, and position. W0, again, the derivative of w0t is also w0 cosine w0t plus phi, and so x double prime is equal to minus xm w0 squared cosine w0t plus phi. Now we substitute this and this in the differential equation, and we get as follows: x double prime plus k over mx is equal to 0, thus minus xm w0 squared cosine w0t plus phi plus k over m x, which is xm cosine w0t plus phi must be equal to 0, and we'll see if this will check. We have two cosines, let's take them as common. Cosine w0t plus phi, identical functions of cosine. Between the parentheses, we have minus xm w0 squared plus k over m xm is equal to 0. Now this obviously cannot always be 0, or else x would always be equal to 0, which doesn't make any sense, because this is different from 0. And now we get that minus xm w0 square plus k over m xm should be equal to 0. Let's substitute for w0 squared minus xm radical k over m. It is given that w0 is equal to radical k over m squared plus k over m xm is equal to 0. And so minus xm, since k over m is positive, it will get off, we will cancel the radical by giving it a positive sign, plus k over m xm is equal to 0. It is very clear that those two are opposites. They will cancel out. 0 is equal to 0, and then yes, it is a solution. This is satisfied. Therefore, x is equal to xm cosine w0t plus phi is a solution for the differential equation. The question continues now to deduce the value of the proper period of oscillation. We know that the proper period T0 is equal to 2 pi over W0, meaning it is equal to 2 pi over radical K over M. And thus, T0 is equal to 2 pi radical M over K. T0 is equal to 2 pi radical 0.5 kilograms divided by 10 newtons per meter. Getting the value of T0 to be equal to 1.4 seconds. Part B. Use the initial conditions and the time equations to determine the values of xm and phi, the time equation being x equal xm cosine w0t plus phi. Let's first identify the initial conditions, and meaning at time equal to 0. The position x initial was 0.1 meters, and the velocity initial, or x prime initial, is equal to 0 meters per second. And so we now know that x initial is equal to xm cosine w0t, which is 0 plus phi. And so 0.1 is equal to xm cosine phi. This is our first equation. And since the velocity initial, or x prime initial, is equal to 0, we know that minus xm w0 sine w0t plus phi, or w0 multiplied by 0 plus phi, is equal to 0, and thus minus xm w0 sine phi is equal to 0. Now obviously the maximum position and the angular frequency are not equal to 0, then sine phi is equal to 0. Now when is phi equal to 0? Phi is equal to 0 when we are at angle 0 or pi, because you know that this is for sine axis and the cosine axis. Then phi is either equal to 0 or phi is equal to pi. Now how am I going to get the right answer? The trick is in the first equation. Since we know that 0.1 is equal to xm cosine phi, and xm being bigger than 0, positive, or xm is bigger than 0, then for all of this to be positive, because this number is positive, the value that will determine the sign of the function is the cosine. Now we know that cosine 0 is equal to 1, which is positive, but cosine pi is equal to minus 1, which is negative, and so this is rejected while this is accepted. Then we can deduce that the value of phi is equal to 0, and thus from equation 1, 0.1 is equal to xm cosine, from equation 1, cosine phi. So 0.1 is equal to xm cosine 0, and so xm is equal to 0.1 meters. We have found the two values that are required for us to find. Use the time equation to determine in terms of t0 the instant at which G reaches the equilibrium position. Okay, this is interesting. Use the time equation. The time equation, which states that x is equal to xm, or 0.1 cosine w0 t plus phi, which is 0, meaning that x is equal to 0.1 cosine w0 t. This is our new completed time equation. To determine in terms of t0 the instant at which G reaches the equilibrium position. Now, what is special about the equilibrium position? The equilibrium position is the position where x is equal to 0. And so we have something to put inside the time equation, meaning that 0 must be equal to 0.1 cosine w0t. And so we know that now cosine w0t must be equal to 0. Now, when is a cosine of something equal to 0? Again, we go to the trigonometric circle. Just this being the sine and the cosine. We know that it is equal to 0 at pi over 2 or 3 pi over 2 or 4 or 5 pi over 2 or 7 pi over 2, meaning that it is a multiple of pi over 2. And so now we know that the cosine function is equal to 0 when the cosine x is equal to 0, when x is an odd multiple of pi over 2. K is equal to 0, 1, 2, 3, etc. When k is equal to 0, x is equal to pi over 2, meaning that we are at this position. When k is equal to 1, we are at 3 pi over 2. 2, we are at 5 pi over 2 going once, twice, thrice, 4 times, 5 times. We are back here. And so it must be an odd multiple of pi over 2. Thus, we reach the conclusion that W0t must be equal to 2k plus 1 pi over 2. Then 2 pi over t0 multiplied by t is equal to 2k plus 1 pi over 2, or t is equal to 2k plus 1 pi t0 over 2 pi. A simple crisscross of mathematics. Pi cancels with pi, and t is equal to 2k plus 1 over 4 t0. By this, the question is over. My dear students, now I am going to explain to you, frankly, the most important part of the lesson, which is to go back to the essence of physics being a natural philosophy. Understanding how is what we are studying is related to the actual world. You see, when we state the word equilibrium, in nature, equilibrium is called the preferred state of nature, meaning how things exist in nature once all of the external disturbances do not occur on them. If they are left alone, how do they exist? Any disturbance or a small deviation to this natural system with the existence of a restoring effect, something that returns it back to its equilibrium position, leads to some form of oscillation. That is, the vibration of guitar strings, musical instruments. Music is created by oscillation, atoms vibrating inside solids. the ocean of the wave, the waves of the ocean. If you can see that the boat on the top of an ocean goes up and down and up and down in a to and fro motion, and so it is oscillating. The vibrations that are caused by earthquakes and even the heartbeat. And so simple harmonic motion is not just a spring problem. It is that nature prefers equilibrium. And they say that nature is lazy by nature. Whenever a system is displaced and there is something restoring it or pulling it back, oscillation emerges. From atoms in matter to music to earthquakes to planetary systems, nature often speaks the language of oscillation. And so it is true that we have studied today the horizontal oscillating spring, but the mathematics used in it can also be used to describe much larger things and much more important things in life. I hope you enjoyed today's session, and hopefully I'm going to see you next time. Enjoy your day, and goodbye.